So BC students, we're into section 9.4, derivatives of vector valued functions. I did post a small video, a short video about vectors, so that since you haven't really seen them much before, just to give you an idea of what they are and how they work. If you've had physics, it might overlap with things that you've learned there, but not everybody has had physics. So check out our classroom page and you can check out that intro to vectors. And if you are someone not able to get to the classroom page, just go to YouTube and see. You'll see that there's lots of different videos that are intro to vectors. So here's some things they want to give you a reminder of about vectors. Vectors have magnitude, which is a length and direction. Vectors can be represented by a directed line segment. Vectors are equal if they have the same direction and magnitude. Magnitude, again the length, is designated by a double absolute value type sign. And they use a V in the middle for vector, not for velocity. Vectors have a horizontal and vertical component. And the component of a vector is in the form of, it's like a triangled off X bracket kind of thing here. So here's what I'm looking at. This would be an example of a vector. It has somewhere where it starts and it goes in some direction. And with that, it has an X component. This is my X component, of course, horizontal. And it has a Y component that's the vertical. All right, so it's got some type of thing. And the way that they designate it is a pointy bracket with the X coming first and the Y coming second, finished by a pointy bracket. And so you can see that all of these things kind of go into play with that. So the first question says, find the component form and the magnitude of the vector that has an initial point of 1, 2 and a terminal point of 5, 4. So if I'm looking at this, all I need to do is remember that I'm going to take the end where it ends, where it stops, right? The end minus the start, where it ends versus where it starts. And the same thing with the Y component. I'm going to do the same thing. Where does it end and where did it start? And that's going to, if I subtract those two things, that's going to be the component of it. So, all right, let's check it out. In our case, I want to go green. You know me and my colors. Okay. I have 5 where it stopped. X stopped at 5. It started at 1. The Y stopped at 4 and started at 2. Therefore, my component vector is going to be 4, 2. That's where it traveled. Now, the magnitude is how far it is, how long it went. In other words, a distance, the length or the distance. Now, think of the distance formula. Remember the old distance formula? Kind of, you almost can see it here. If I were to close this Y part in over here, then I would see I've got a right triangle, Pythagorean theorem, all those things coming together. So if I want to find the magnitude, all I need to do is take the square root of the X component squared plus the Y component squared. So let's do that. If I take the square root, my X component is 4. My Y component is 2. When I square root them, I get the square root of 20. I could reduce that or simplify that. 4 times 20 means it's 2 square roots of 5. I'm sorry, 4 times 5 is 20. The square root of 4 is 2. So 2 square roots of 5. That would be another way of saying it. And this would be, if I go back up here, that would be what my length of this thing is. Sometimes you'll see it listed like this with an R. The magnitude is designated by a double absolute value kind of thing. With what sometimes they'll use an R. You have X, you have Y, and then you have the R. Sometimes they'll use it R's, and you can see that actually in the next couple little things here. So vector valued functions are functions in the form of R of t, where you have the X component is f of t, the Y component is g of t. They're your parameter for t. And the differentiation of value vectored functions, if they give you a function like this and they want you to take the derivative, all you need to do is take the derivative. So r prime of t would equal the vector f prime of t as your x component and g prime of t as your y component. That's it. Take the derivative of each piece. And then the next thing that comes into play are the properties of properties of derivatives for vector valued functions. So easy to say, right? But they're all the same things you know already. So I'm going to kind of give this a little whirl. We know if we have a constant and I'm trying to take a derivative, I need to bring the constant down in front, keep the constant there, take the derivative of the r function. If I want to take the derivative of a polynomial, then I just take the derivative of each piece. If I have to multiply two pieces together, then the product rule comes into play. And if I have something like this, like the chain rule, then it's going to be r prime of s of t times s prime of t. It's a chain rule thing. Don't forget all those little derivative rules that are applied. All right, so r of t is this. Find r prime of t. And you say, okay, I can do that. R prime of t equals the derivative of each piece. So take the derivative of the f function, the x value, and the derivative of the y value. This is really easy peasy, kids. 9t squared minus 4. And guess what? That's the answer. You're done. That's it. All right, so then they say, now this one I found to be a little bit more tricky. And I don't think it came up in the practice problems, to be honest with you. But you see how this is a 2t? We're going to have to, that means that I'm going to have to take the derivative of that 2t in the end as a chain rule, which is something that I don't know that I would have thought of necessarily. So let's check it out. The derivative, to take the derivative of this thing, find the derivative. This is just a notation for the derivative. We're going to go with just r prime of t first. That's the same as we did in number 1. It's going to be 3t squared as my x component, and my y component's a 2. Now, what I really want to find, though, is r prime of 2t. All right, so watch and see how this works. It's going to be take your derivative you just took, put in a 2t instead of a t. However, then I need to chain rule and take the derivative, times it by the derivative of 2t, which is 2. So watch and see what happens with this. 2t times 2t is 4t squared. 4t squared times 3 is 12t. I'll take you in small doses here. 12t squared, comma 2. But that has to be multiplied by 2. So my final best wonderful answer for this, times it by 2, is 24t squared, comma 4. And that, my friends, would be your r prime of 2t. So figure out what the derivative is for the original vector, and then plug in that 2t, but remember to chain rule it and multiply by 2 as well in the end. And then number 3, this one is your last note problem, the last example problem. The path of a particle moving along, the English of this is lovely. The path of a particle moving along a path in the xy plane is given by the vector valued function t squared sine of t. Find the slope of the path of particle at 3 pi over 4. Well, slope, what does slope mean? Slope means derivative. All right, if that's the case, then I have to find the derivative of this thing. So let's find f prime of t. F prime of t. 2t, derivative of sine is cosine. Cosine of t. There it is. That's not bad, right? So I'm going to take that derivative, but I have to remember that slope is actually, that might be the derivative that I'm looking for of the vector, but slope puts it into a form of the change in y over the change in x. Well, if that's the case, remember dy over dx, if I put it that way, then I have the cosine of t up top and I have 2t on the bottom. You see how I'm just adjusting that from a vector into a slope form so that I can literally figure that out. All right, well, what t value do I care about? I want to evaluate that when t equals 3 pi over 4. All right, so that's going to be the cosine of 3 pi over 4 over 2 times 3 pi over 4. So I go to my brain and I think, all right, well, 3 pi over 4 on the unit circle, where am I? What's that coordinate? And that coordinate is negative square root of 2 over 2, positive square root of 2 over 2. Remember, any of the 4s are going to be this. It's just a matter of what quadrant it's in, so that you can then put the appropriate signs on it. So cosine is x. That means I have, I'll write it this way first, negative square root of 2 over 2 divided by, this would be 6 pi over 4, 3 pi over 2. But ain't nobody like a complex fraction, so therefore we're going to change this thing and go horizontal. So I have a negative square root of 2 over 2 that's being divided by 3 pi over 2, or negative square root of 2 over 2 times 2 over 3 pi. Keep, change, flip. 2's cancel. Final best answer is negative square root of 2 over 3 pi. And that takes care of the note problems, the example problems for this. I'm going to pick just a couple of the practice problems to show you, and then we'll be done. First practice problem I picked is number 2. All right, here comes number 2. I have the directions say each problem contains a vector valued functions. All right, find the given first or second derivative. Well, in this case, they want me to find the first derivative, and they want me to find the first derivative when my t value is pi over 6. So here I go. Find the derivative first, f prime of t. If I am a 3 cosine of 2t, I am, derivative of sine is cosine, so I am a 3 times sine becomes cosine, cosine of 2t, chain rule times 2, and the second part becomes a 4, but it's going to be a negative sine of 3t times 3. Now let me clean that up before I put in my pi over 6. So this becomes a 6 cosine of 2t. This becomes a negative 12 sine of 3t. It's not going to give me much room in the box, but it's okay. All right, so I want to know what f prime of pi over 6 is. So let's now plug it in. 6 cosine of 2 times pi over 6. This is a negative 12 sine of 3 times pi over 6. Again, I'm going to clean it up one more time. Pi over 6 equals, this is, now 2 pi over 6 is like pi over 3. So I have to think of pi over 3. I'll go up above. Can you still see me up above? Let me pull it down a little. Actually, I can go into box 4. It's all, we're not going to do number 4 together. All right, so I have 6 times the cosine of pi over 3. I have negative 12 times the sine. 3 pi over 6 is pi over 2. So there are two coordinates that I need from my unit circle. The first one I need is pi over 3. Pi over 3, if I'm thinking my coordinates, I go up. It is a 1/2 square root of 3 over 2. And the other coordinate I need is pi over 2. Well, pi over 2 is at the top, so that is 0, 1. Now with that information, I should be able to fill this in, because cosine is the x value. That means this is 1/2. Sine is the y value. This is 1. So here I go. I'm going into this other box. I'm being a rebel. So I get 6 times 1/2 for my x component, and negative 12 times 1 for my y component, and I can finish this finally out. Half of 6 is 3, and negative 12 times 1 is negative 12. There it is. There's my first derivative at pi over 6. Next one I wanted to go to is very similar, however, you're going to see it requires a little bit more savviness, and that's number 7. So number 7 is my next choice down here. Same idea, right? It wants the same. You're like, yo, Wenner, you're picking the same problem over again, but I'm really not. You'll see. Pi over 2 is what I want to find the first derivative at. And so in the midst of this, here's my t sine of t, t cosine of t, and here's the problem. And hopefully your red lights are going off. Do you notice that that's a product rule? T sine of t. t sine of t cosine of t. So we've got to treat this one a little bit differently. To find the derivative, I'm going to find f prime of t first. That gives me, are you ready for this? This is going to be long. Write small. The first times the derivative of the second plus the second times the derivative of the first. Well, the derivative of t is just 1, so there's my x component. My y component is the first times the derivative of the second. Well, that's a negative sine of t plus the second times the derivative of the first, which is 1 again. So we need to know, now we could do a lot to clean this up, but really any t value is going to come in and you're going to replace it with pi over 2. I want to know what f prime of pi over 2 is. That's going to give me pi over 2. Every t is replaced by pi over 2 times the cosine of pi over 2 plus the sine of pi over 2, x component. Y component is negative pi over 2 sine of pi over 2 plus the cosine of pi over 2. All right, so let's think about the unit circle. If I'm at pi over 2, I'm up at the tippy top. We just talked about that in the last problem. My coordinate is 0, 1, which is sweet because when I replace that into this hot mess, it's going to actually turn out okay. So let's see if we can do that. F prime of pi over 2 is pi over 2. Cosine of pi over 2, well, cosine is the x values times 0. Plus the sine of pi over 2 is the y value, that's a 1. X component. Y component, negative pi over 2. Sine is the y component, so that's 1. And cosine is the x component, that's 0. All right, so let's finish this out. I have 0 times pi over 2 plus 1, that gives me a 1 for my x component. Negative pi over 2 times 1 is negative pi over 2 plus 0 is a negative pi over 2. And so you have just completed that. But that one required the product rule in the midst for your derivative. All right, so that's what made that one a little bit different. Next one I picked, last one I picked is number 10. So come with me to number 10, and then we will be done. The position of a particle moving along the xy plane is defined by the vector-valued function f of t equals yada yada. For what value of t is greater than 0 is the particle at rest? All right, let's go back to AB calculus and think about, all right, well, when is a particle at rest? What do I do? So if it's at rest, it depends on the first derivative. Makes sense it would be in this section, right? It's at rest when the derivative equals 0. Hopefully you remember that. Remember, it's moving right if the derivative is positive, it's moving left if the derivative is negative, and it's at rest if it's 0. So that's kind of all flowing together. All right, so let's figure this out. If I think of the derivative, I'm thinking of dy over dx. That's my derivative. So in other words, I need the y component on top, the derivative of it anyway. That's going to be 6t squared minus 18t minus 24. And my derivative on the bottom is 3t squared minus 12t. I want to know when that derivative is equal to 0. Okay, so if I set it equal to 0, a couple different ways you could think about this. You know me, I'm big on cross multiplying. Put this over 1, cross multiply. It ends up however you want to think about it. Some kids think about it as multiplying both sides by 3t squared minus 12t. Either way, your next step's going to be 6t squared minus 18t minus 24 equals 0. The denominator gets banged out of there. And so let's solve it for t and see for what values of t is it at rest. Let's keep going. Take out a 6. T squared minus 3t minus 4. If I factor that, t minus 4, t plus 1. Set them equal to 0. The 6 out in front means nothing. T equals 4, t equals negative 1. Right? They're my two values. However, if I look at those, for what values of t is greater than or equal to 0 is the particle at rest. This guy's extraneous. It's not in that domain that they're giving you. So your only answer, and I don't want to box it, is t equals 4. So I'll say it this way. So t equals 4 is your final answer. And that, my friends, is section 9.4. and I will join you again for section 9.5. Have a great day. Email me if you've got questions.